Early stage of infection. Oh. This one has got- I didn't see anything. Hide in there. Do you want to connect to this? Do you want to do your slides?
That's okay. Mine aren't really slides.
Okay.
Are
you sure?
I'll put what I have up online, and then we can take note of it.
Are you sure you don't want to do this first? Your thing?
It would take a couple time.
Yeah? What are you preparing them for?
The panel?
With the multiple choice questions?
Yeah, it's like.
Well, that might be more interesting than my thing, my summary. What you guys prefer?
Summary.
Well, if you're gonna put it up,
I'll put what
Post-
I have online and make my vote.
Okay. All right. Early stage of infection. Number 1. No.
Yes,
Yes?
from this presentation there.
He is generous. I wouldn't put the answer. I was like, go ahead and find out the answer.
The way it's set up, it's incorporated into the slides, so you'll see.
Very generous. Number 1. It enters the cell through receptor mediated fusion. Right? Then, number 2, partially uncoats. Why is partially uncoated? Inside of the capsid, what does it happen? You have reverse transcriptase, which is bound covalently to 3' and complete double-stranded DNA, right? Because it is a partially double-stranded DNA virus. Very important to say that. That's partially double-strand, because that's a key difference on this, right? Important to say that. All right, and then number 3, virus migrate to nucleus. How do you think this thing gets inside the nucleus? With the help of nucleoproteins, right? I just wanted to put this out there. Number 4, in the nucleus, it unpacks and how many messenger RNAs are transcribed?
4.
4. 4 messenger RNAs are transcribed using what? Who transcribes these messenger RNAs, guys?
RNA.
RNA polymerase 2. RNA polymerase 2. Plus the whole machinery that goes with RNA polymerase 2. Right? Are those RNAs, let's talk about 4.1 here. Let's talk about the characteristics of those messenger RNAs. Are they capped? Yep, they are. So they're capped. They're capped. Do they have poly A tails? Yes. Are they all the same size? No. They're different. And where do they start? Where they are different? On the 5' or 3'? 5'. So 5' and divers. And this leads to different lengths, right?
Sorry. On number 3, you said virus migrates to the nucleus. In the lecture, you said the genome migrates to the nucleus, so it's still inside the actual capsid when it's going into the genome?
Yes.
Okay.
Is this contrary to retrovirus? Where is the capsid in retrovirus? Is the capsid in the nucleus or is it outside the nucleus?
The retrovirus, the capsid is outside the nucleus. When it gets to the nucleus, the capsid gets into the nucleus and then gets dissolved by proteases. Yeah, viral proteases. The capsid gets dissolved by cellular proteases when it gets close to the nucleus. And then the genome gets inside with the help of nuclear proteins.
So the capsid doesn't enter into nucleus?
No, here the capsid does not enter the nucleus.
But for retrovirus, the capsid does.
Yes, retrovirus capsid enter the nucleus. This capsid does not enter the nucleus because it needs plasma, cytoplasma proteases to dissolve the capsid. There is no proteases inside of the nucleus. It needs the proteases of the cytoplasma to dissolve. That's why.
The olive one is too. Is that for the host? Some kind of host.
All right.
I have a quick question for 2. What did you mean by partially double-stranded DNA in the parentheses?
Here?
The next
Here?
Yeah.
Because remember, it's not completely double-stranded.
Oh, okay.
So it enters, you have, remember, you have the negative,
For this one, it does not enter the capsid. But just the gene does, then they have to go to the
negative DNA, right? And then you have the positive DNA. But it's partially double-stranded. This portion here is single-stranded. That's what I mean by.
Okay.
Yeah?
Yes, thank you.
And that's
I'll go through. I'll go through. I didn't get there yet.
yeah.
All right. So, okay, so those are the messenger RNAs, right? Now, remember that this messenger RNAs, we're going to have different kinds of messenger RNAs. We have 2 general kinds. So we have messenger RNAs that are going to be responsible for proteins for the excision, right? We're going to produce core proteins. We're going to produce envelope proteins. Remember that? Yeah? We're going to produce LM proteins. Yes? Okay. And we're going to have messenger RNA that is a positive C messenger RNA, which is a full length to be used as a template. Right? It's, in fact, is larger than the cDNA itself, right? To be used as a template. And notice that this all has to do with the late stage of infection. So we're transitioning to late stage of infection. All right. Yes.
The 4.2, so there's 4 mRNAs, and then you said 2 go to make the XSLN protein, right?
I believe it's 3.
Oh, okay.
3 or 2. I think it's 3 goes for that and 1 is a full length, yeah.
Okay, and that's
So you have 2.7, 2.1, and 0.7.
And then, so the remaining full-length mRNA, is that the cmRNA or makes the cmRNA? I just want to know what...
There is the cRNA, the remaining, the 4th one.
Okay.
Mm-hmm. Question?
I just wanted to clear, so it's the early stage of infection is 1 through 4.1, and the 4.2 is when it starts beginning with late stage of infection, or are you just stating that just to come back to it? I'm just trying to figure out chronology.
What is where?
Yeah.
Where is where? Okay, so let's do it. Okay. Early stage of infection is until we get into the nucleus.
Okay, and 4 is late.
Number 4 is kind of like an intermediate stage of infection, right? We're in the middle of the process yet. We're producing messenger RNA so we can translate those messenger RNA so we can make proteins to get out. Then, on number 5, which I'm going to go next, that's the late stage of infection.
So here was this 4.2, we're talking about the mRNAs, and then we go into complementary mRNA. Each 4 pre-mRNAs going through that step. Is that correct? So
What do you mean by each of 4?
So,
You have 3 messenger RNAs produced that will produce those proteins to get out. And then you have 1 that's going to be bigger than the DNA itself, that's going to work as a template to make the genome to get out. Okay. So number 5. Now I will answer your question. So this is the replication we go from positive C messenger RNA Can you guys grab me another color if you find? If it's not, look at the other side. You can open too and look in the pocket inside. No? There is a pocket in there. I'll grab it. We need other colors now. Yeah, sure. Thank you so much. Did I leave in the classroom? Yes, I did. I left in the classroom. Never mind. All right. So we have a full-length messenger RNA that I am going to put 3' to 5'. Yeah? Then this full-length messenger RNA, and I'm going to put it here, a PBS sequence because that's familiar for you, all right? We know that. And then we have a transfer RNA that binds in plus our RT plus RNase H. So then it is binding to the 3'. Do you see that? And then it's going to go to the 5'. So this one is going to be 5 to 3. Once it reaches an R sequence here, and you copy our R sequence, this will have a halt. Bless you. It will stop and then it will jump. So this is step 5.1. Right? So I'm going to put it right here. when transfer RNA plus RT plus RNase H reaches R sequence, stops, and jumps. 2, the second homologous R sequence on the positive C messenger RNA. So the other sequence is right here on the 3' end. So this whole thing, plus the little bit of DNA that was made, all together jumps right here. Okay? All right, so I'll erase this portion of intermediate stage so I can draw in, okay? Okay? I'll erase this part. So the whole, so the whole thing jumps. So I'm gonna have the 5' RNA to 3' C positive C messenger RNA. And now I have R sequence here, I have R sequence here. Now my whole complex jumped and I'm matching. See, I copied R here, so I'm matching R with R. And then I have a PBS here, right? That was copied in the beginning. And now here I have a transfer RNA. I have an RT, reverse transcriptase, plus RNase H. I jumped the whole thing. Are we good? And now I need to copy the remaining. Okay? All right. So now I'm going to copy the remaining. But I'm copying 2 chunks. Therefore, I need ligase.
For retroviruses, do you need a no ligase?
Different kinds of RT.
Oh.
Now,
Just to clarify,
Yes.
so the first strand you drew, it copies to that R region and then it jumps to the other
yes,
and copies until it reaches the first.
that's right. Same
So-
process for retrovirus, with the exception of ligase.
So for number 5, this is the late stage.
Yes,
Okay.
late stage. Because now I'm making the DNA to be packaged inside the capsid so the virus can leave the cell. All right, so that's 5.1. Okay, I made negative sense. The black is negative sense cDNA. Sorry, the pen is not working. Negative sense cDNA. Yes? The black one. So now RNase H is going to degrade this whole entire thing, with exception of the primer region. A little section of the RNA. So the whole thing is going to be degraded. So I'm gonna write in blue, just let you know, this negative cDNA, but I will label, okay? Okay. So I have 5' to 3', and this thing is negative cDNA. I have one little portion right here remaining of RNA. That I'm going to use as a primer. Yeah? And then what is going to happen is the transfer RNA plus RT plus RNA ASE, and let's make it a note in here too that RNase H degraded positive messenger RNA. It's degraded. With exception of that PP, right? So now, this entire thing is going to hop 3 to 5. So it's going to go that direction. It's going to read 3 to 5 and make it 5 to 3. So this is 5 to 3. Do you see that? Yeah? Are we good? Okay. And this is the positive DNA. But when he reaches the step, it doesn't jump again. It doesn't have the second jump like the retrovirus. Remember the retrovirus reaches PBS and then it stops and jump again? This doesn't. And that's why the thing ends up partially double-stranded. Then, meanwhile, what do you have too?
Is there like an advantage to that?
To be partially double-stranded?
Yeah.
Good question. Maybe the only thing I can imagine is speeding up the process. Making it faster to get out. But that's it.
Is that PP or PBS?
It starts on PP.
Okay.
In retrovirus, it starts in PP too. But it will stop in PBS.
Okay.
Well, what are the implications to have like a double strand? Because remember, for the previous, for just completely double stranded, it was supposed to prevent degradation, but it was harder to separate. But having it double stranded make it easier to separate.
So you're saying that the fact that it has partially double
Yeah,
stranded
so
is easier to separate. That's
to
a
be
good
able to
one.
faster process in order for
Very good,
transcription.
Kiana. Very
So
good.
it
Make
makes
a
it-
note of that.
Could you say that one time?
Yeah. Go ahead, Kiana.
Oh,
Dr. Kiana, please.
for like in the when we just learned about double-stranded viruses, when it's just completely double-stranded, it was harder for it to separate and to continue on for transcription because it evaded the
So it's
cellular
stable.
immune system because it was double-stranded, wouldn't get degraded. But this partially double-stranded DNA will allow it to have a faster transcription. And
Because it's already
it's already
partially
like
unwinded.
yeah, it's already partially unwinded, partially exposed, and it can kind of evade the immune system in that way because it is double-stranded. So it's just kind of like easier transcription and slightly better way to
Okay.
evade the immune system.
Let's put that in here because I'm gonna take a picture and post it. So let's put it down in there. Oh, I'll put in the advantages when we're done with this. Don't let me forget. Okay. All right. So then, that's 5.2, right? And then 5.3, genome replication is completed when reverse transcriptase is bound to 3' cap. Now, the genome can be packed inside of the proteins that we already translated, because now we have time to have all this translated, right? And the virus bugs the cell. So number 6, bless you, genome is packed inside capsid and buds of the cell. Of the cell with envelope. All right. So now you have the summary of the material down. So what's your next step? Advantages and disadvantages.
I have 3 questions.
Yes.
So, why would you produce the protein first in the genome?
What, like the negative RNA virus?
Oh, okay.
Yes.
2 is, okay, I lost that one. But 3, so like the stuff that you put in your slides, would you prefer us to like kind of like use these versus the ones that are in the slide and do a combo?
Use
like,
this.
This one?
Mm-hmm.
Okay.
Use this.
The maturation of the capsid, that like breaking things?
Maturation of the capsid is this, completed when RT is bound to the 3' cap. That's the maturation of the
And
capsid.
that's also when the partial positive stops.
Yes. This also helps on the biochemical signal to stop.
For the adenovirus, so when it's
For the
inside
adenovirus?
yes, yes, for
Mhm.
the when it's inside the nucleus and it's replicating the capsid, is it like hijacking the nucleus because the retroviruses has integrases and resolvases?
Yes.
Does this one have integrases and resolvases?
No, we don't know.
We don't.
We don't know. I think it does, and we don't know.
But it's still hijacking the nucleus.
It is hijacking the nuclear machinery, but we don't know if it's integrating on the genome or not. But the fact that it causes cancer suggests that it is, right? Integrating to the nucleus, to the genome, to the cellular DNA. Because otherwise, how would it cause cancer? If it doesn't modulate cell proliferation, if it doesn't increase cell proliferation, how would it cause cancer? So somehow, some way, it needs to modulate cell proliferation to be positive of cancer. Now, how it does it, we don't know. Maybe it's through a biochemical signal. Maybe it's not through integration of the genome. It can be that way too. But we don't know for certain. All right.
In my notes, I have that for transcription of the P protein, it doesn't require a tRNA as a primer. The protein itself serves as a primer.
Yes, it does. Yes, it does. You're correct on that. The transfer RNA, that's for the retrovirus. But I wanted to draw a parallel because that's what you know for now, so you can understand. But here, the P protein together with the RT is the P protein is instead of the transfer RNA.
Does that say MOS right there in black?
Say again?
Does that say MOS in black right there on the bottom?
PBS.
Oh, PB. Oh.
So what you have there next to the reverse transcriptase is P protein, right?
P protein.
P protein.
Instead of transfer RNA is P protein for this virus.
The PBS, is that just like the, you said it was like the stop or
It's a protein binding sequence.
Okay.
That's for the beginning.
at the beginning?
Yeah, that's the beginning. But on retroviruses, it's also responsible for the second stop
Okay.
in retrovirus. But this hepatitis virus does not do a second stop. It ends in there and that's it. It ends in there, it receives the signal of the maturation of the capsid and it stops right there.
What is the purpose of the PP sequence?
It's a primer sequence.
Okay.
And that's where the P protein or the transfer RNA knows where to restart.
What's the purpose of that part not degrading? The PP.
Oh, the PP for now, because it needs to start with a primase, RNA primase. It's like the beginning of the zipper. The same situation happens on our DNA, right? We have RNA primer. And then later on, RNase H will dissolve this, will take care of that and remove this. But for now, it's the beginning. So you can have the P protein or the transfer RNA binding to it and continue transcription from there. Good questions. Okay. So now you know the material. So the second portion is to see how is this advantageous for the virus. Right? How is this advantageous for the virus? We talked about this already. How is it advantageous for the virus, right? Now, the fact that it's partially encoded, the same advantage when we talked about the retrovirus. How is that advantageous for the virus? Protection. Virus migrating to the nucleus. Protection. Then, the fact that it produces 4 different kinds of messenger RNAs using RNA polymerase II. How is this advantageous to use the cell RNA polymerase II? It has the ability of capping to do poly-A, and it's there. It's already available. It's made. So it expedites the infection, right? And it's already there. Then, also, the fact that it's capped and has a poly-A tail, it will disguise among the messenger RNAs produced by the cell itself. The fact that we can produce in different lengths is the same advantage as